So there is a question on homework 3.3, number 3, and number 20 is similar. I believe we talked about one of these in class. I don't know if it was this one exactly. So you're given the graph of two functions, and h, capital H is 3 times f plus 4 times g. And what we want to do is find the derivative of h at 1. So remember, when the derivative here, h prime of 1, that means find the slope of the tangent line on the function h when x is equal to 1. Let me just capture this. Okay, so it involves a couple of things. We've got to know certain derivative properties to take the derivative of capital H. So if we look at h prime, what would h prime be? Well, we need to find h prime of 1, right? We need to find that. So we have to have the h prime function to plug 1 in before we are able to determine that.
It would be 3f prime x plus 4g prime x.
Yeah, so we've got a constant times a function of x. The constant comes out, we differentiate the function of x. We're not given f of x, so we're just going to say it's f prime plus 4g prime. I mean, both of these lines have y-intercepts, and we've got a grid. You could certainly determine the equation of the lines, but it's not even necessary. So when we evaluate h of 1, sorry, h prime of 1, we have 3 times f prime of 1 plus 4 times g prime of 1. And then we've got to recognize, well, if I'm asked what f prime of 1 is, I'm just asked at the x value of 1 on the function f, what is the slope of function f, right? Because that's what f prime measures, the slope of f at 1. So we go here at 1, and we go up to function f, and we say, all right, well, what's the slope of this curve or this function here at 1? So we just need to measure the slope. They're linear because the slope doesn't change, and it's easy to compute. You couldn't probably ask a question like this if you were given like curvy functions, because it would be impossible to tell how to measure the slope. So we can measure the slope of f at 1, which gives us f prime of 1. Does that make sense? F of 1, the slope of f of 1 is f prime of 1. So what do we have? We have, we go down 1, to the right 2. So we have a, well, this is what we're doing. So we have our rise over our run, negative 1 over 2. That means we've got 3 times the slope here at 1 is negative 1/2 plus 4 times g prime. Do that again, g prime of 1. Again, what's the slope here at that point? Yeah, so we can go, it's always the same, so we can go up 2 and to the right 1. So the numerical value, whatever we get there, that is h prime of 1. That's going to be 8, so we'll call that 16 over 2. So So there's h prime of 1. Anybody have any questions on that? It's really about derivative rules, albeit it's a bit abstract. And do you know what it means when we evaluate a derivative at a point? All right. Yeah.
Could you do number 11?
It's 3.3 as well.
3.9.
3.9. This was number 3, I think, and 3.3. 3.9, 11.
Math lab was really finicky about the,
Final answer.
yeah, about how it wanted it simplified.
Yeah, so we can check it out to see how they want it simplified. So like, yeah, I don't know, it's frustrating to do some of these problems because these functions that are like f of x to the g of x power, sometimes they want them simplified in a specific way, and sometimes they don't. There really doesn't seem to be a lot of consistency, which is frustrating, because some of them you can just enter in, it's fine. I guess one like this, you enter it in and it says, no, that's not correct, they want you to simplify it. So as far as the test goes, if we can just get the basic answer before simplification on how my math lab wants it, you'd be totally fine. But we've got, there's two ways to differentiate a function like f to the g. One way is to rewrite f of x in terms of e in the natural log. So we can say that f of x is equivalent to e to the power of the natural log of 8x. We'll just do this. Natural log of 8x times natural log of sine x. This looks like really familiar. So bear with me for a moment.
That's fine.
Because there was a question on this earlier before we looked at logarithmic differentiation. And then once we talked about logarithmic differentiation, I believe we went back to that problem. So yeah, this was from our notes in class. So I'm not going to work it out again. We've already worked it out. This was the answer that we said, that's fine, don't simplify this. So yeah, it's exactly the same. So you can get all this in our example. Or we could use second method from our notes in class. We could use logarithmic differentiation. I think it's the same problem. Yeah, it's the same problem. Use logarithmic differentiation. See. Okay, so once we find the derivative, it wants us to evaluate the derivative at the given value of a. So I'm assuming that they're prompting what's the derivative, and then they want you to evaluate the derivative at a to give, whatever that number is. I assume that's what it is. Okay, yeah, so they want you to find the derivative function. It says use parentheses to clearly denote the argument of each function. So can let's just try to enter what we had for in class. There's going to be a lot of parentheses. It's just really tedious. Cotangent x plus ln sine x over x. Oh, so it didn't want us to simplify. It just wants us to clearly use parentheses. So it's like an overuse of parentheses, to be honest. Like you would never write it out like that. Okay, so let me put this in our notes, just because you should definitely try to get the answer that we got, but here's the answer in its full parenthetical glory. Yeah, so all right. And then the only other thing we need to do is plug in pi over 2 for the x's here. So and the natural log isn't going to yield a nice value for pi over 2, but we could see a cotangent. We could get a value for cotangent at pi over 2 and sine for pi over 2. Yeah, so sine of pi over 2 is going to be 1, so the natural log of that's going to go away. So it probably won't look as hideous as we think it might. And then we'll evaluate. Evaluate this. So we'll just write it out. Sine of pi over 2, and it's that value raised to the natural log of 8 times the pi over 2 power. So here parentheses for our power. And we have that number times all of this stuff. So the ln of 8. Plus the ln of pi over 2. And those two numbers times the cotangent of pi over 2. Plus this number, which is the ln of the sine of pi over 2 over pi over 2. So like we said, this one here is, this turns into the natural log of 1, which is equal to 0. So that whole thing is 0. On this number on the outside, we have sine of pi over 2 is what? 1 to the power of whatever this mess is, 4 pi over 2, ln of, 4 pi rather. What's that going to be? 1. 1 to this number is still 1. So that's 1. I'll leave it like it is for now. 1. Then we have what's the cotangent of pi over 2? Is what?
0.
0. So all of this is 0. All of that 0 plus all of that 0. So we have 1 times 0 plus 0. Not bad. So if the derivative on this function, whatever it looks like, if the derivative is 0, what does that mean? What happens on the graph?
It's flat.
It's flat because you have the tangent line is what?
Horizontal.
Horizontal. Yeah.
Oh, I was just gonna ask for a different problem.
Okay. So that what that says is that on that function at pi over 2, you know, you've got like a parabolic shape, whether it's opening up or down. Yeah.
That,
Which one? Me or him? You nodded, and I was trying to figure out which one you were. We both had our hand raised.
Oh, I guess I was looking at you, but I didn't see something.
I was going to say I have another question too. I'm not sure where his question is at, but mine is also in 3.9.
Okay.
Before we move anywhere, I
mine's
guess.
still about this problem.
All right, yeah, we're going to stick with this problem for the time being. So let's just evaluate f of pi over 2, just so we can see where that point's at clearly. So we're going to plot the point pi over 2, 1, just so we know this is on this function. This is where we're finding this point. It's where we're finding the slope of the tangent line. So we can see it's at one of those peaks. So we would expect the tangent line to be horizontal right there, which is what we got. Okay. What was your question, Luke?
Oh, it was, could you keep sine pi over 2 to the ln 8x, I guess could you keep that as e to everything? Is e to the power of all
Yeah.
that? And you'll still get the right answer?
Right.
Okay.
Remember, if you use this, it's still going to be the same answer because you'll end up with e to the 0 here, which is 1. Remember this e to the ln 8x, ln sine x? That's equivalent to this sine x to the ln of 8x. So whether you had this or this in your final answer, it doesn't really matter because it's the same.
Okay.
I was also going to ask, because I know when I was solving that one, it was giving me a bit of a hard time. Instead of separating the ln 8 and the ln x by adding them together, those two logs, couldn't you just kept them together and then use
Yeah.
the first one and the second one, just made a product out of that? That way you don't have to have some parentheses.
Yeah, I honestly personally think it's easier to have call that ln of 8 plus the ln of x. I would have just left it as the ln of 8x. But we were just trying to be consistent with our notes in class, where we said simplify completely with logarithms. But yeah, that's certainly ln of 8x times cotangent. We could have that as. Yeah.
Can you just tell me how that last part of the function is?
The ln sine over x, because the sine of pi over 2 is 1, but the natural logarithm of 1 is equal to 0. Yeah. So yeah, it's we've seen a few questions regarding the natural log, and it's a lot of them can be easily remembered by or answered by just remembering the graph of the natural log. And here's the point on the x-axis 1, 0. So when we plug 1 in, we get 0. And that was like really the only main point on that graph. I mean, there's other points, but they're all weird. Yeah. Any other questions about this one? All right, what What was your question?
3.9, number 15.
So use logarithmic differentiation to evaluate. We could use the quotient rule, and we have the quotient of two functions. Each quotient rule, when we do the derivative of the top and the derivative of the bottom, that's a chain rule. So you've got a quotient rule and two chain rules involved here. If you just took the derivative normally with derivative rules. So I'm just gonna call this y. That way we can start out with taking the natural log of both sides. Okay, so take the log of both sides, and then we're going to simplify the function in terms of x as far as we can with properties of logarithms. So what would this look like? We would first break this up. Let's just do it one step at a time. Our first kind of tearing apart of the function with properties of logarithms would be it's a fraction, right? Log of a fraction is equal to the difference of logarithms. So the natural log of the top, minus the natural log of the bottom. Okay. There's one more thing we can do with that, because we're taking, in both of those, we're taking the log of something that's raised to a power. So the powers can come out front to multiply the log of x plus 4 minus the power out front multiplying the log of 3x minus 6. Is everybody okay with what we've done there? So now it's totally simplified. Honestly, you could have gone from here and said, all right, well, I'm just going to take the derivative of that. But applying logarithmic differentiation and not simplifying fully, it's kind of, a lot of times it's just kind of redundant, right? Because you still have a quotient rule, or sorry, you still have a chain rule with both of those. Two chain rules. Here we're just going to have like one chain rule involved when we take the derivative of the 3x minus 6 now. Okay, so once you've simplified completely, then that's when you take the derivative of both sides. Okay. So now we have y prime over y is equal to 11 over x plus 4. Remember, the derivative of the natural log of x plus 4 is 1 over x plus 4 times the derivative of x plus 4, which is 1, minus, we have our 10 times 1 over the argument times the derivative of our argument, derivative of 3x minus 6 is 3. So we have y prime over y is 11 over x plus 4 minus 30. We could probably we can simplify that to 30 over 3x minus 6. So notice we can take out a 3 on the bottom and divide the 30 by that 3. So let's just do that so it's a little bit easier. So y prime over y we have as 11 over x plus 4. Plus, or minus rather, minus our 30 over the 3 times the quantity x minus 2. Okay, so that's that's how we're gonna just simplify that. I guess it's not really a necessary step, though. Okay, so we have that simplifying to 10 over x minus 2. Is everybody okay with the derivative stuff here? That derivative. Any questions? All right, then we solve for y prime. Multiply through by the original function. Whatever that was. Maybe we're able to do 11th and 10th. Yeah, 11th and 10th. So just leave it like that. Any questions on that? It's definitely a weird process when you first start doing these things, but I think once you get accustomed to them, it's much easier to use this process than applying, multiple derivative rules, for sure.
But can you go over so you multiply y prime over y times y?
Yeah.
You have to do it to both sides. And y equals 11x plus 4 minus 10x. That's y?
No, y was given to us, it was whatever that original function we started out with was. So that's y or f of x right there.
So shouldn't we put that for the final answer?
Mhm.
Shouldn't we put that in the square brackets?
Well, no, because remember this is y prime over y is equal to this right here. And then to solve for y prime, we're going to multiply by y on both sides.
Yeah.
So you've got
Oh.
yeah, you've got
Okay,
your
never
y
mind.
times.
I just saw it. I'm so
Yeah,
sorry.
That's all right. Yeah, it's all kind of funky.
Okay.
Yeah, no worries. I'll leave that there. Yeah. Any other questions on that? All right. Yeah.
I have a question, 3.9, number 13.
Equation of the tangent. So, so hopefully at some point when you're, doing your homework or reviewing your homework, hopefully at some point you're looking over this stuff without the help of my math lab help me solve this or view an example. Oops, there it goes. Just a little slow. Like on the exam, you don't have those tools, right? So like at some point, I think initially it's fine to use those to get an idea of like how I should proceed with a certain problem. But when you go back and review, even if when you review your notes, it's sort of detrimental to look at just what we did in class, how that problem was worked out. If you're looking at a question and using as a review, you should work that kind of blindly, because you want to know like what can I do, right? I don't want to know on the exam what the computer can do or what the teacher could do, right? It's got to be what you can do. So you've got to practice that retrieval at some point in order to be successful. A lot of people will say like, hey, I studied for like 12 hours for this exam for like 3 days, but it's not how much you study, it's kind of how you study. And what I see a lot is people like do study a lot, but they're studying the wrong way. you've got to be able to get to some point where you're doing this stuff on your own and doing it correctly without any sort of aids, nodes, MML or otherwise. That's what I would recommend to you. However you go about that, I don't think it really matters, but you know, that's honestly how I studied for all of my exams. I would just do all of the problems in the back of the book, of each section, and then I would look at the answers. So did I get this one right? Why did I miss this one? And you know, there wasn't that instantaneous feedback, so you have to go through your problem and say, well, why did I miss this? And then you slowly start picking apart your errors and thinking your errors in computation. And then when you're tested, it's all there. Like, you can totally retrieve all of that information because you weren't assisted with that information. But study how you want, I guess. I'm telling you how to study, I just know what works, I guess. So equation of the tangent line at the point x equals to 1. So it's really, you know, misleading. When we find the equation of the tangent line, we do need a point. We only have the x value of that point. So we have to, you know, plug in to get our y value. But also the equation of the tangent line involves the slope of the tangent line at that point. So we need that piece of information, and we need the slope of the tangent line at x equals to 1, which is f prime of 1 or y prime evaluated at x equals. So what's the cotangent of 1? It's not a nice number, is it? No one's reaching for the calculator. But it's not a nice value, like the cotangent of pi over 2. We know what the sine and cosine of pi over 2 is, you know. The cotangent of 1, what's the sine of 1? What's the cosine of 1? You know, it's not a radian measure. So we're just, what's 1 to any power though? 1. Some of these might have like a variation where, you know, your point could be, you could just say your point might be like 1 comma cotangent of 1, and you just leave that cotangent of 1 like that. You wouldn't actually say, well, it's 1 comma, you know, point, whatever. Okay. But for us, that doesn't apply. It could apply though. Like some of these questions I've seen where they have, you know, like a y value that's not exact, so they just leave it in, you know, it's mathematical terms, I guess. I don't know how to say that. But this is the point 1, 1. x1, y is 1. Now we just need to find the derivative. Again, it's a function to another function's power. We can rewrite in terms of e and ln, or we could just do logarithmic differentiation. We take the log of both sides, the power rule pulls the cotangent out front to multiply the logarithm. So unfortunately, like, we still have a product rule on the right-hand side, but that's it. There's product rule, there's no chain rules. Both of those arguments are just x. So take the derivative, y prime over y. Take the derivative of this side first, times the derivative of the second, plus the second, times the derivative of the first. What's the derivative of cotangent?
Secant squared.
That's the derivative of tangent. Derivative of tangent is secant squared. So what?
Negative cosecant squared.
Negative cosecant squared, right? Remember, the derivative of tangent is secant squared. So when we look at the cofunctions, we replace the functions with their cofunctions and make the other part negative. So, you know, if you're only remembering that the derivative of tangent is secant squared, then you get the derivative of cotangent, because I'm going to replace this function with its cofunction. I'm going to replace secant with cosecant. And I'm going to make this negative. So that was just the rule for replacing functions with their cofunctions. So negative, we'll put that here, our negative cosecant squared. y prime is then our original y prime is our original function times this piece right here. All right, any questions on where we're at? We had to use the product rule, and then we multiply through by the original function. Now we just need to find y prime at x equals to 1. So 1 to the cotangent of 1, like we said, that was already 1. We have cotangent of 1 here. Over 1, I guess we'll just put all this, minus the ln of 1, which is going to zero all this stuff out. So we have a cotangent of 1 minus 0 times 1, and that just gives us cotangent of 1. So did anybody compute cotangent of 1 yet? It's a radians. I'm just curious, it's not, it's going to be some approximation, but we're going to leave it as cotangent of 1 since it's not. Is that what you got? 0.62.
642.
642. 096? 0926. And then the number just is like an irrational number. It would keep going, which is why we're not going to put this in for the slope of the tangent line. We're going to put this in for the slope of the tangent line. So the equation of the tangent line is going to be y minus y1 equals to the slope of our tangent line times x, times x minus x1. Whatever, we'll just leave it blank. So that would this one and this one were from the point, right? The original point. The cotangent is the slope of the tangent line.
So to solve that, was the product rule used?
To get the
Yeah.
part of purple?
Yeah.
Yeah.
So I was wondering if it was a product rule, shouldn't it be like a plus in the middle instead of a minus, or am I getting it wrong?
Yeah, the minus, originally it's a plus, but remember what we had was that the derivative of the cotangent was negative cosecant, and or negative cosecant squared, sorry. And since that was multiplied by the natural log, it made it negative.
Okay.
Yeah, so that negative there will make it here. This negative here. Okay, so then from here you just solve for y. Is that okay? Yeah.
Does ln 1 times the cosecant square 1?
Yeah. Yes. Again, we have a natural log of 1, which is 0. Cosecant squared of 1 times 0 just give us 0. So you'll have y equals to, how do I write that? Cotangent of 1 times x as the equation of the tangent line. or, well, I guess it would be minus cotangent of 1 plus 1. So slope of our tangent line times x. And then we have this minus cotangent of 1. And then we add this 1. So it's, you know, this is the equation of the tangent line. We're not calling cotangent of 1 by its numerical value. So we just have that in as sort of the number, right? The y-intercept is negative cotangent of 1 plus 1, and the slope is cotangent of 1. So that's what this looks like. And this, all of this stuff is RP. It could be a positive number, I don't know. I think it is, because it's 0.642. 1 minus 0.642 is what that number is, approximately. Any other questions about that example? Okay. Move along. I'm just gonna call this homework 3.9, since most of the questions were from 3.9. That way, when you look it up, remember we had that first question from 3.3. So yeah, 3.10 is where we left off. We were pretty much done with 3.10, derivative of inverse trig functions. I think perhaps we'll look at one more example. Remember, as far as the exam goes, all you're going to have to do is match. All you're going to have to do is match these functions with their derivatives. All right, we saw in that last example that we didn't need the absolute value here. So originally what we have on this first line with y prime was just the derivative as it's told us, the formula as it told us to take the derivative. But we didn't need absolute value around the square root of x, since it's always positive. And this square root of x and the square root of x here in green just multiplied to give us x, and then our square root of x squared under the radical was just x. So we were able to simplify that a little bit. Other times, sometimes you have to leave the absolute value. So remember, just the purpose of the absolute value was to ensure that whatever we're inputting or applying to a function is positive. So if we know it's always positive, absolute values are redundant. We've got to keep them when there's potential that the thing could be positive or negative. So like, for instance, if y were the inverse secant of 2x, so we're just going to take the derivative, how the formula tells us to take the derivative, and then we'll determine, do we have to leave the absolute value or can we remove it? So the derivative of inverse secant was what? How do we take it? We do 1 over absolute value of
x times the square root of x squared minus 1.
Yeah. So that's for like if the inverse secant of the argument was x, right? So just replace your x with our argument of 2x. So yeah, 1 over the absolute value of the argument multiplied by the square root of the argument squared minus 1. And then we do what? So that part's just from the formula here. What else do we have to do?
Decide to keep the absolute value.
Definitely need to decide that, but this isn't a complete derivative. Why?
Don't you have to multiply it by the derivative?
Yeah, the chain rule. We have the derivative of the inverse secant part right here with the inner function left alone, and then we have to multiply this by the derivative of the inner function by the chain rule. Just like we did with the square root was our argument. We still had that stuff, but then we had to multiply by the derivative of the square root. So the derivative of 2x is going to give us 2 multiplied by all of this stuff. And we can call that 4x squared minus 1. So can we get rid of the absolute value here with 2x? You've got to think about it a little bit. The derivative, of course, is based off the domain of the original function. And the original function's domain is going to tell us where x is. So we have to say, all right, well, if I know if x is always positive, right, then 2 times that positive numbers is always positive when we don't need absolute value. But if there's potential for x to be positive and negative, especially negative, we have to leave the absolute value around 2x. So the argument is 2x. And what we said was that the domain of the inverse secant function was the absolute value of the input has to be larger than or equal to 1. So the domain here of this whole function, the inverse secant of 2x, is that the absolute value of 2x has to be larger than or equal to 1, which means 2 things. That 2x has to be larger than or equal to 1, or 2x is less than or equal to negative 1. Right, that's how you solve an equation in an absolute value inequality that's greater than or equal to. Does everybody remember that? Maybe been a while. So if you have the absolute value of something is less than or equal to a number, and we can replace less than or equal to with less than, so it's both. Then what that means is that this quantity is less than or equal to the number, but it's greater than or equal to the negative of the number. So that's sort of where you get like a sandwich. You have a connected interval where your solutions are. Whether it's greater than or equal to, I don't know, would affect these. But when you have an absolute value less than a number, you've got like this completely connected interval. When you have the absolute value of something greater than or equal to, or just greater than a number, it's that thing on the inside is greater than or equal to the number, or that thing on the inside is less than or equal to the negative of the number. And so what we have here is kind of this scenario. All of this stuff and all of this stuff. So this is the one where you have like disjoint intervals. So anyways, 2x is greater than or equal to 1, which means x is greater than or equal to a half, or x is smaller than or equal to negative 1/2. So there is potential here for x to be negative. Since x can be negative, 2x can be negative, which means we can't remove the absolute value here, because 2x can sometimes be negative. So let's write that. Since x is, what did we say, less than or equal to negative 1/2. 2x can be negative. Thus, we need to keep the absolute value around 2x. So that's our, we're going to say that's our simplified derivative right there. All right, does anyone have questions on that? Yeah, they don't, the ones on the test don't get this advanced. You just have to match the basic derivatives to the basic functions. I think it's good to talk about this stuff because you see it on your homework, and it forces us to have to like recall old information from other classes. So that's, if no one has any questions, we're going to end 310 right there. Okay, then we're going to move on to our last two sections, 3.6 and 3.11. That's all of the derivative rules. I mean, there was a lot, but 3.6 and 3.11 deal with a lot more simpler derivatives than most of this stuff. So 3.6, we're going to talk about derivatives as rates of change. And then we're going to look in 3.11 at related rates. So we're going to have a lot simpler derivatives compared to a lot of the stuff we've been doing once we hit 3.6 and 3.11. The main formulas from 3.6 are going to be a couple. They're going to be the displacement. So displacement is defined as, usually S is position. Our textbook notes S as position. So this delta S, we're reading that as basically it just means a change. Is that delta? So a change in position, which is given to us by S. And I think really the important thing to distinguish here is that displacement and the total distance you've traveled isn't the same. Like if you drive to school and then you drive back home, say it's 10 miles from your house to school, right? You've traveled a total distance of 20 miles, 10 there and 10 back, but your displacement is 0 because the position at the start and the position at the end are the same location. So displacement is just a change in position. The position at the finish minus the position at the start. So we're going to look at displacement. We're going to look at speed, velocity, and acceleration defined in terms of derivatives. So this is where we get derivatives as rates of change. We saw that in chapter 2 early on, where we said let's look at the average velocities, and then we'll look at the instantaneous velocities. So that's a rate of change. But specifically now we're going to tie these three things together. So suppose an object moves along a line. So we're talking about a straight line, left, right, up, or down, with the position function S equals f of t. I'm not sure why they chose to denote it that way. I think it's just, in practice, it's just s of t is your position function. They're just trying to be a little bit more generic and say the position is just any function of t that you want to label it. Okay. So we see what the formula tells us here, but if we measured a, let's say hours, time on the x-axis, and miles on the y-axis, and you're tracking something's position over a course of time. So maybe it looks something like that, I don't know. When we find the derivative at a point, when we find the slope of the tangent line, let's say at this point, what are the units for that slope? Yeah, the units are, remember, this is going to be the slope, which is also the same thing as the derivative, which is also the same notation as dy over dx, right? So a small change in y over a small change in x is what the derivative is. So when you calculate this derivative, its units are just going to have units of y over the units of x. So if you start off measuring a position, and on that position you calculate the instantaneous rate of change or the derivative, then it's going to give you a rate, miles per hour, which is, for us, we usually call that a speed, but it's technically not our speed, it's our velocity. So that's what we see here. The velocity at time t, velocity is just the derivative of the position function. So s prime of t. That's the way we're going to think about it. The velocity function is the derivative or the rate of change, instantaneous rate of change of your position function. Notice then the acceleration is the derivative of the velocity function, or the second derivative of the position. So acceleration is the derivative of velocity, which is the derivative of velocity is the second derivative of the position. And speed here, speed is just the absolute value of the velocity. Function, whatever velocity is. Okay, does anyone have any questions initially here on what we're doing? When we get into chapter 4, we'll look at this in reverse. So here in chapter 3, it says, hey, here's the position function. What's the velocity? What's the acceleration? By derivatives. In chapter 4, we'll start off with an acceleration function, and it'll ask, based off of this acceleration, what's the velocity, and then what's the position? So we kind of work backwards in chapter 4. Another thing worth mentioning here is that when we take, for speed particularly, for speed, when we take the absolute value of a function, so I don't know, let's say this is our function. When we take the absolute value of that, the absolute value of the velocity function, what would that look like? What would the graph look like? What does the absolute value do?
Makes everything positive.
It makes everything positive, right? So guess what? All of this stuff that's positive is just going to stay positive, but all this stuff that's negative, it's going to be positive as well. So that's all of an absolute value graph would do to the original function. Anything below the axis just puts it above. Anything above stays the same. Okay, some of these other formulas we don't really deal with. We're primarily focusing on the velocity, speed, and acceleration. But there's countless other applications. Here are two. We can find average and marginal cost. That's something you would see in like a business calculus class. Elasticity, something you would see in an economics class. You can look at the back of this section to see other applications of derivatives as Richard series. There's just basically any quantity you can think of, there's an application of the derivative to that. Whether it's temperature or heat or whatever. We're going to look at a few examples. The types of problems we want to focus on for the exam, I'll mention once we get there. But I think before we start this section in full, we're going to take a break and then we'll come back to 3.6. We might, depending on how fast we can get through this, we might have to do a little bit of 311 on Thursday as well. So it might cut into our review time because I don't think we can do both today. It's sort of like one-dimensional motion that we're looking at, motion along a line. In example 1, it says a police station is located along an east-west freeway, so that's our line. At noon, when time is 0, the patrol car leaves the station heading east. This is the position function of the car. S is f of t. Gives the location of the car in miles east for positive positions when S is positive, or gives the location of the car in miles west when S is negative after t hours after noon. So like this statement here, the location of the car is in miles east or west of the station. Like for example, if we have like the position function evaluated at, this isn't relevant, we don't have a 40 for our input, but just to kind of get a sense of it, if S of some input time is equal to 10, then what that actually means is the position is 10 miles east of the station. Or if like S of 15 were equal to -6, then again that means it's 6 miles west of the station. That's what that statement is clarifying. We want to answer a few questions. We want to, part A, describe the location of the patrol car during the first 3.5 hours of the trip. And here's 3.5 hours after noon. So here, what's happening at that point? Where is that person?
At the station.
At the station, right? That's given to us. They start out at the station. So we're just going to write that. Starts at the station. Then what? What's happening here?
Travels east.
Traveling east. Again, how do we know they're traveling east? It's positive, right? All of those positions are positive. 10 miles east of the station, 20 miles east, 30 miles east, 40 miles east, etc., etc. So they travel east for how long?
1.5 hours.
Between one and two.
Yeah. We travel east for 1.5 hours. Then what happens? They stay there, right? Their position is not changing. They're 80 miles east of the station, and over that period, that green period of time, their position's not changing, which means they have to be sitting still. stops for how long?
Half an hour.
For half an hour? Then what? Okay, I guess that's cool. Right, so even though the positions are positive here, right, like this person is still heading in the opposite direction. So like we would say at this point, they're still 40 miles from the station. Like they traveled all of this way, but then they're coming back, is what we see as the return trip in that yellowish color. So then they travel. And I guess we could be more specific here with the red trip and the orange or yellow trip. We could also specify like how far they travel, right? So they travel east for 1.5 hours, but we can see that they stop at 80 miles from the station. They travel east 80 miles of the station for 1.5 hours. And then this orange path here, they're traveling how many miles?
100.
100, right? Because this is, once they reach this place right here, again, that's back at the station. So that's an 80-mile trip in the opposite direction. But then they continue going, here are negative positions. Then they continue traveling west for another, looks like these tick marks are 10. So that's -20. So then they travel back to the station, which is west. That's 80 miles, which puts them back at the station. And continues another 20 miles west of the station. Does that make sense? So any sort of one-dimensional motion like this is you know, as time unfolds, you're going to see it as like a two-dimensional thing, just because we put time into the mix. We're no longer measuring just a position like this, going back and forth. We have that position measuring up here, but time is down here now. So we get this sort of, you know, two-dimensional aspect from it because time's in the mix. Okay, so that's the first 3.5 hours of that trip, and again, that's all the information we have. So, part B asks us to calculate the displacement and the average velocity of the car between 2 p.m. and 3:30 p.m. So our displacement, remember, was defined as delta S, change in the position. So it's the position at the end minus the position at the start. Which is, for us, it's the time or the position at 3:30. The 3:30 corresponds to a t-value of what? So it says that second sentence, at noon, time equals 0, the patrol car leaves the station. So 3:30 corresponds to t equals, yeah, 3.5, right? If noon is 0, then 3.5 hours, 3:30 is 3.5 hours later. So the position at 3.5 minus the position at the start, which is at 2 p.m., which is 2 hours after noon. Does that make sense? Anybody have any questions on that? So we use the graph to determine that. Our position at 3.5 is -20. Because remember at 3:30, they're now 20 miles west of the station, so it's negative. And we'll write our units here. Negative 20 miles, and we're subtracting off S of 2, and S of 2 was position at 2 hours was 80. So positive 80 miles. So that change in position, the displacement is negative 100 miles. So why is it, what does the negative mean?
Traveled west.
It was in the westward direction the whole time. So from 2 to 3:30, like we described in this gold portion on part A, they travel west 80 miles, they're back to the station, and then they travel an additional 20 miles. So there's 100 miles, and the negative indicates west. So there's our displacement, the average velocity. No. The average velocity. How are we going to find that? We'll call that V average.
You'll divide that number by the difference of the inputs.
Yeah.
Like the distance of time.
The change in time, right? Remember, velocity, like we said, is just a position over a time, miles per hour, meters per second. So it's a position over a time. So the average velocity then is defined as the displacement, change in position, over the change in time. So we already have the change in position from 2 to 2:30. We just calculated that, right? That's S of 3.5 minus S of 2 divided by the change in time, 3.5 minus 2. So we know that top came out to be negative 100. And again, our units for this one were miles. The change in time is positive 1/2. And then that's, 1.5, my bad. So 3/2. And then that's measured in hours. Okay, so we have negative 100 over 3/2, or negative 100 over 1.5. So that gives us something in miles per hour. What was that? Negative 66.6 repeating miles per hour. So why are we saying it's negative 66.6 repeating miles per hour? What does that mean? Yeah, they're going west. So remember, speed is the absolute value of velocity. They're traveling at 66.6 miles per hour, but the negative indicates direction. As with any velocity, the sign of that number will indicate a certain direction. So that means they're traveling 66.6 miles an hour west. Again, we knew that from the displacement. The time, we wouldn't expect the time to be negative. All right, so there's our average velocity. Which means, as that person, after that person stops and then travels back towards the station, that on average they're traveling 66.6 miles per hour. Any questions about either of those? And then what time or times is the instantaneous velocity the greatest as the car travels east? So we know the car is traveling east on that red portion. This is when they're traveling east. So the question says, when is the instantaneous velocity the greatest on that interval? And we can rephrase, I guess. That's from 0 to 1.5. So we could also say that question is, at what t value or values is the, or this word here, slope of the tangent line the greatest on the interval from 0 to 1.5. That's what that question's asking. Since we don't know the equation of the function, all we have, we're stuck eyeballing it. So these questions are sort of ambiguous, but we can certainly look at that on that red portion. Where does it seem like the slope of that portion is the largest? Is it going to be here, or is it going to be here, or is it going to be here? You know, like where is that? Definitely not at the start. So all of the slope here is flat, this slope is that, this slope is that, and then they just start getting steeper, right? But then here they start leveling out.
About to say, could you say from 0.5 to 1?
Yeah, that's probably what I would say. So like, you know, from here to here, somewhere in there, meaning we're looking at the slopes here, somewhere in there they're the greatest, because when it first starts out it sort of like curves up slowly, and then after that it sort of to bend down to where it's flat. So I think that's perfectly acceptable for a question like that. To say that the instantaneous velocity is the greatest when, I don't know, t is in between 1 and 1 and 1/2. Can't really identify exactly where, but we can sort of get close. So they could be, you know, that could be at like 0.6 hours, it could be like 0.75 hours, it could be 0.72 hours. But that's about as best as we can do. Do y'all have any questions on that example? Yeah.
Would you say like a vertex is 0.5?
Yeah, I guess, but our x's, our independent is actually t though, so.
I was gonna say, like, if something like this was on the test, would the question be more specified to what intervals instead of just what time is the instantaneous velocity to the greatest?
Yeah, and honestly, I won't ask a question like that because I think it's too vague. There's, you know, some person might put 0.75, some person could say 0.62, somebody else could say an interval, you know what I mean? I mean, I could specify, you know, what interval, but I'm just avoiding those ambiguities altogether. Example 2, sort of similar. We've got a different kind of scenario, but we've got a position of an object that's moving horizontally at time t, measured in seconds, given by the position function t squared minus 5t. And then it says t is in between 0 and 5. So we're only looking at the first 5 seconds of whatever this thing's doing. Assume that positive values of position correspond to positions to the left, or sorry, to the right of S of 0. It's very similar to that. Now we're not talking about east and west, we're talking about left and right. So we want to graph the velocity function and determine when the object is stationary, when the object's moving left, and when the object's moving right. So that entails graphing the velocity function, entails that we find the velocity function. So what is the velocity function and how do we find it?
It's the derivative of the position function.
Right, like we said on the first page, velocity is just the derivative of the position. So our velocity function is 2t minus 5. Just linear function. We're only going to graph from 0 to 5, but it does have a y-intercept here at -5. And it's got this positive slope, so it'll look something like this. That's v of t. We're just exaggerating the endpoints here. Okay, so we've got the graph of velocity. When is the object stationary? How would we answer that? When the velocity is 0, yeah. So stationary when the velocity is 0, which is right there, the or the t-intercept. Stationary when the velocity is 0. That stationary then at time equals to 5/2 seconds. When is the object moving left? So it said, all we have is that assume positive values of position correspond to the right of its initial position, which is at 0. But, so we could graph t squared minus 5t from 0 to 5, see where that quadratic function is positive and see where it's negative. But we're looking at the velocity graph. So it's usually a matter of convention, and it's always consistent. So it might not be intuitive here, but moving left is when the velocity is negative. So we need to figure out when velocity is negative, which we can because we have the graph. And then moving right is when the velocity is positive. It's all a matter of how you've set up, like whatever you're measuring, you can determine when the time starts, and you can determine whether positions to the left mean positive or negative. But usually it's just by convention, so it's a little bit more intuitive. Because it's just based off of the values that are to the right of 0 on the axis are positive, and values to the left are negative, that kind of thing. So moving left when velocity is negative, and it's negative on what interval?
-5 to 5/2.
-5 to 5/2. And so we've got to determine what that interval looks like, right? Are we including the endpoints? Are we excluding both? Are we excluding one but not the other? So is the velocity negative at 5? Sorry, that should be -5, right? What should that be? 0, that's a time value. The -5 is the velocity value. So we're describing a time interval. So do we include the time at 0?
Yeah.
Yeah, it's definitely negative. Velocity is definitely negative at 0 here. Right here. What about at 5/2?
No.
No, we would exclude that because it's what? It's stationary, right? It's neither positive nor negative at 5/2. So a similar thing, when is it moving to the right? Well, it's from 5/2 to 5. We're including the 5, and we're excluding again the 5/2. Any questions on that? Part A. Part C says graph the acceleration function and determine the acceleration of the object when the velocity is 0. So how do we find A of t then? How do we find the acceleration function?
Take the derivative of velocity.
Take the derivative of the velocity function. So the derivative of our 2t minus 5 is just 2. Let's talk about acceleration here in this instance. If we start off with this position function, time is in seconds and position was not given. Oh, in feet. So this is our position. All right, when we look at the rate of change of position, we have the velocity, and the units of time are still the same, but the units of velocity are, since it's the derivative, are the y units over the t units, or the s units over the t units. Velocity in feet per second. And then when we look at acceleration, acceleration is the rate of change of velocity. So what are the units for the acceleration?
Per second.
Yeah, feet per second. Remember, so like to get the units for acceleration from velocity, we just divide the y units by the x units, right? So we have feet per second, right? So feet per second squared. And it's when you see a velocity, negative 9.8 meters per second squared. That's what it means. It means negative 9.8 feet per second every second is that change. Okay, so the velocity then is constant at 2. I'm going to get rid of this and just graph our velocity here. Or sorry, our acceleration. I'm going to graph A of t from 0 to 5. We'll just stop that here. And it's always at 2. So there's our acceleration function. And then it wants to know what's the acceleration when the velocity is 0. Yeah, it's always 2. Acceleration is always 2. But we know the velocity was 0 at 5/2, so like right here somewhere, acceleration is 2. Oops, it is 0. And then part C asks, when is the speed increasing? So if we go back to the first page and we define speed as what?
Absolute value of velocity.
Absolute value of the velocity. So that's easy enough to graph. We have our velocity function here, which was, we have the velocity function here, doing something like this. So the absolute value, the speed. Here we'll mark this again, that was 5/2. This piece is still positive. The reflected up, so this is now at. So there's our speed. When is it increasing? Speed is increasing on the interval from
5.5 to 5.
5/2 to 5. Do y'all agree with that? 5/2 to 5. Are we including 5/2? No. Are we including 5?
Yeah.
Yeah.
So yeah, here I think, you know, at this point, our speed is still increasing, right? So it's almost like I can see arguments either way, but it depends on how intervals of increasing, decreasing, and constant are defined. And if you remember that they're usually defined only on open intervals, because it doesn't make sense to say you're increasing at a point, right? You need some sort of length or distance to determine whether something's increasing or decreasing or constant. But that's how MML is going to answer this. If you said it was increasing on 5/2 to 5 on the open interval, I wouldn't count that wrong either. Because I personally feel that these intervals of increasing, decreasing, and constant should be open intervals, not. I mean, this is still an open interval, but we're including the endpoint. So anyways, that's what we would say there. Anybody have, yeah?
Why are you including 5 around 5/2?
Because 5/2 it's 0, right? So it's neither increasing nor decreasing. But if we looked at the velocity and say, well, the velocity is increasing here, from here to here, and even at this point, there's really no indication that it's like just dying off or staying flat. You know what I mean? So like we're just gonna assume, yeah. But like I said, I'm okay if you have parentheses around both. Any other questions on this question number 2? And question 3, this would be like an exam question. So this is, we'll just say it's exam content. And so what we have is a stone being thrown upward with initial velocity of 64 feet per second and from a bridge that's 96 feet above the river. The position of the stone after t seconds is given by our position function, s of t, where s of 0 is the level of the river. So when position is 0, you've reached the river. So it's like, here's the river, here's this cliff that's 96 feet above, and you know, somebody's standing up here throwing something off. So find the velocity and acceleration functions. So fortunately we have a position function, so to find the velocity and acceleration, we just need to apply the derivative. So the velocity, we take the derivative of the position. So power rule, negative 32t to the first plus 64t. Or sorry, plus 64, no t, is the velocity function, and then the acceleration is the derivative of velocity, or the rate of change of velocity. So this acceleration would, our velocity would have units of what? Velocity's units would be what again?
Feet per second.
Yeah, feet per second. We're given that too. Velocity is 64 feet per second. What are the units for acceleration?
feet per second squared.
Yeah, feet per second squared. Feet per second. And then after acceleration becomes jerk, so the units there would be feet per second cubed. And then the other subsequent derivatives, feet per second to the fourth, which again, all of it are just further subdivision of the feet per second. Feet per second, and then feet per second, right? So it's really weird to think about it. If you think about it too much, it'll probably make your head hurt, but it's kind of cool to think about it. It's just really interesting. So we've got our velocity acceleration functions, and then we're going to be asked certain questions about position, velocity, or acceleration. But the main thing is that we've got all three functions. So whenever you're asked questions about either position, velocity, or acceleration, just keep in mind that they are functions of time. So if we need the velocity at a certain instance, it boils down to you always have to find the time in which that particular event happens, and then plug that back into whatever function you're trying to answer about. So, like, what's the highest point above the river reached by the stone? We have to find what time it takes for the stone to reach its maximum height, and then we figure out its maximum height. In part C, what velocity does the stone strike the river? Well, we have to first figure out when the stone hits the river, and then we plug that into the velocity. So all these questions asking about acceleration, velocity, or position, they always boil down to finding a time that something happens first. The highest point above the river, I guess there's really two ways we can answer that, because we do have a quadratic position function. So the highest point above the river, one, let's just list our options. One, we could do what? What seems reasonable to do? Yeah.
Find the vertex.
Find the vertex, right? So like this stone being thrown off a cliff looks like that. It's quadratic. The highest point occurs at the vertex. We can find the vertex. Specifically, the point that we have on our position function is measured in seconds, comma, feet for our position. And it's asking what's the highest point above the river. So we really want the y coordinate of our vertex. Okay, what's the other option?
I was about to say, could you use negative b over 2a?
Yeah, so finding the vertex, that's what our formula is. It's negative for quadratic, negative b over 2a, and then we would evaluate the position function at that number. That's the vertex for, well, I guess we have t's. Okay, so we could find the vertex. What else could we do?
You can find the velocity to 0, because then it's not moving.
Right, yeah, exactly. What's the slope of the tangent line here at the highest point? 0, right? So, in a mathematical sense, we would say that the slope of the tangent line on the position function at that location is 0. But we know the slope of the tangent line in this setting is the velocity. So when is velocity equal to 0? Notice here you come up with a t value, and then we're going to plug that t value. That t value here, solve for t, that t value is going to be this t value of the vertex. So however you go about it, you're going to have to find this t value, or the vertex negative b over 2a, exactly the same number. So these two things are exactly the same number. And then we have to plug it back into the position function to determine exactly how high is it at that particular time. find out where v of t is equal to 0. Solve for t. Plug that t into the velocity function. Or sorry, into the position function. So with either option, you get the same result. I think it's probably easier to figure out where the velocity is equal to 0. So we'll just do that one. So that's a 2, when a time value of 2 is when that stone reaches. So 2 seconds after we throw that is when that happens. And then so we're plugging this into the position because we want to know something about the position. So negative 16 times 2 squared plus 64 times 2 plus 96. What do we get? 160 feet. So that's the maximum height reached by that object. Does anyone have any questions? Okay, what about part C? With what velocity does the stone strike the river? How are we going to figure that one out?
If you set the position function to 0, and set up top that when the y value of the original function is 0, it
Yeah.
hits the river.
Exactly. So here, when the position is 0, that's the level of the river. So whenever position is 0, that's corresponding to the location of the river. So what we have to do is figure out first what time is the position 0, and then we have to plug that time into the velocity because we're trying to answer velocity. So S of t equals to 0, solve for t, plug in velocity. Okay, so our position negative 16t squared plus 64t plus 96. So where does that equal 0? You can try to factor, we can probably factor out, you can use the quadratic formula. Either way though, solving quadratic, by factoring we're using the quadratic formula. I'm not going to waste a whole lot of time with this. So negative 1.162 and 5.162. Is what we get from the quadratic. So what are we plugging into our velocity?
Those two numbers.
Those two numbers,
Positive one.
a positive one. Right, because we, just by convention, you start measuring when your watch reads 0, right? You're not gonna like dial your watch back to like negative 5 seconds to start. I mean, you totally could. Your initial position and everything would be based on a time value of negative 5 if you did that. But the time value of whatever it was, negative 1.162, this is a time value of 0 here. So like what's happening over here at this time value? Don't know, you can't go back in time, so negative time values. Typically, at least in like, a lot of most straightforward like physics applications, like negative times don't make sense. Unless it's specified, hey, this event started at negative 12 seconds, then it would make sense. So we're then gonna evaluate our velocity at 5.162. And so that was the, what, negative 32 function plus 64. So that's the the time it takes for the stone to reach the river, and then we're now measuring the velocity at that particular time. So negative 101.84. What does the negative indicate? Yeah, it's moving down. Like the object is falling to the ground. You know, so it starts off, you throw it up, it's going positive, it stops, and then it's negative. Just like that east-west kind of thing. What are the units? Yeah, velocity in feet per second. Okay. Any questions on that? So you have something similar-esque on the exam from 3.6. Just one of those.
One of these questions with all the sections.
Yeah. Yeah. So I'll ask you what here's the position function, what's the velocity, what's the acceleration, and then answering questions about positions, velocities, and acceleration.
So the acceleration is always
Yeah, in this situation, it would be just because things are falling to the earth, no matter how high they start off, and just like the x-y axis, down is negative. You could certainly orient it the other way and say anything that's negative means that it's moving up, but that's not how it was set up originally. So yeah. Typically, these things are always like intuitive. I guess, I don't know. I guess it's intuitive to think that negative is moving down. I don't know. All right, any other questions? We're gonna skip that last example because we're running behind. All right. We'll definitely have to finish 311 on Thursday. Already have it. Okay. So 311 deals with related rates. And what it is we're relating rates to one another in like these sort of fixed patterns. So like, you know, if an example is like if you've got a cube whose sides are length 1, we want to know how fast the volume of that cube is changing when the cube's sides are 5 inches long or 5 meters long. Like example 1 says there's an oil rig that has sprung a leak with these certain conditions attached to it. We want to know how fast is the area of that patch increasing. So all of those kinds of things, we're relating rates to one another because, like in a circle, the rate of the radius versus its area are changing. It's always a fixed relationship. The cube, the side length versus the volume is always fixed. So before we start though, the related rates, the independent variable here is always time. So all variables and functions are differentiated implicitly with respect to time. So even if you see an x, if you call something x and you take the derivative, you have to call it x prime because it's with respect to time. So all variables with respect to time. When we substitute variables, you only want to do that after you have differentiated your fixed relationship between the things. So like you've got a fixed relationship between the side length of a cube and its volume. a fixed relationship between a circle's radius and its area. Those are the relationships we establish first. We differentiate that stuff, and then we plug in or substitute our variables. Okay. Any rate will be like meters per second or miles per hour or feet per second, etc. So those rates will always correspond to something's derivative. So there's a couple of figures for, I think at least this first example, just so we can kind of get a sense of what we're measuring. Have to find it. I thought I had them, but I don't. Okay, so let's see if it's exactly the same. Might be exactly the same. We have an oil rig that sprung a leak in column C's. The oil spreads in a circular patch around the rig. If the radius of the oil patch increases at a rate of 30 meters per hour, how fast is the area of the patch increasing when its radius is 100 meters? So it sounds like a lot. I guess they're not going to animate this up here, but here's the oil rig. This is the radius, this little arrow here, and then so as time progresses, we see that it just grows and grows and grows. So what we want to do is we want to find, we want to know how fast is this area, the total area, increasing the moment its radius reaches 100. So, like right at this moment, somewhere in there, we want to know exactly how fast the radius is changing. It's like a frozen moment in time, right? At a particular time, how fast exactly was that area changing? So we're going to look at what we're given, and like we said, any rates of change that we are given, those are going to be a derivative. So it says that the radius of the oil patch, the radius is increasing at 30 meters per hour. So what do y'all want to call the radius? What letter? R. Seems natural. We're going to call the radius R, but what are we given with 30 miles or 30 meters per hour? Is that the radius? No, it's the rate of change of the radius. So we want to call that R prime. You know, I typically don't write of t because all variables are functions of t. But if you need to write R prime of t, then write that. So we're given that R prime of t is 30. So the other question is, are these rates of change, are we going to label them as positive or negative? And it really depends. Is this 30 going to be positive or negative, and why? Just sort of intuitively.
Positive.
Positive because
It's increasing.
it's increasing. The radius is positive 30 because that the rate of change of the radius is increasing. Okay. So that's all. So what we're given is that. What we want to find out is how fast is the area increasing. So what do we want to call area?
A.
A. All right. So area. How fast is the area increasing? So is that a rate we're measuring, or are we just measuring something static? It's a rate, right? How fast is the area increasing or decreasing? That's a rate. So we want to know what A prime is. So A prime is what when the radius is 100 meters. So we'll just write that again. Our radius is 100. So that's what's given to us. Given the rate of change of the radius and a specific radius, what we want to do is find out how fast the area is changing. So that's what's given to us in that problem. Now, we need to, with all of these problems, you've got to establish a relationship. We're going to establish the relationship between the area and the radius based on the area of a circle, because it's a circular patch, right? So here's our relation. We'll just call this our relation. Area of circle. Area equals pi r squared. Remember, area and radius are both functions of time, though. So what we have is our relationship is really a of t equals to pi r of t squared. Does that all make sense? Does anyone have any questions or comments? So you establish a relationship between the things you're given, and then to establish the relationship between their rates of change, we have to take the derivative of our relationship implicitly with respect to time. Differentiate with respect to time. So what's the derivative of the area with respect to time? So that's like our function of x, right? That's like f of x equals to pi x squared. Or sorry, pi f of x squared. So when we take the derivative of a function, how do we denote the derivative? Just denote it with a prime, right? Derivative of the area function is a prime. So we have a prime of t is equal to, what's the derivative of pi times r of t squared? 2 pi times r of t times r prime. Implicit differentiation. This is an unknown function that's being squared. Power rule, the 2 comes out front to multiply the constant. We leave the inside function alone, and then we multiply by the derivative of the inside function. If it were a squared in our formula, the derivative would be the same. It's 2a prime. Questions on that derivative? There's derivative with respect to time. It's no different than we said, okay, well, y is a function of x squared. How do we take the derivative of that? It's 2 times f of x times f prime. Same thing with the radius. So we set up a relationship, we differentiate. Now we have the rates, the derivatives related to one another, and now this is where we would plug in our variables. So you find your relationship, you differentiate it, and then you plug in what you're given. Plug in given info. So we were trying to figure out what a prime of t was. So that's our unknown, a prime of t. We're solving for that, but we know that the rate of change of the area is 2 pi times the radius. R of t, we were given the radius, is 100. Times the rate of change of the radius, which we were given as 30. So times that is 30. Remember the rate of change where it was, the units were meters per hour. the units attached to the 100 are meters. So there's nothing to solve for. We have A prime. Whatever that number is. It's 6,000 pi. 6,000 pi. And our units are meters times meters per hour, or meters squared per hour. Which is what we would expect from an area, right? Square meters per hour as a rate of change of the area. And that's approximately 18,850 meters squared per hour. So that's a pretty massive amount of stuff. I don't know if this was modeled from a real situation or not, but oops,
Well, sounds like it.
approximately 18,850 meters squared per hour. Just so we have a sense of what that number is. But there's our exact. All right, so, start the homework if you want, look over that example and think about what we've done, and we'll finish this on Thursday. As well as review for our exam, so also come to class with any test questions you might have.